Okay, so the first talk this afternoon is by Bernard Teissier, and he'll talk on zero-dimensional valuations on equicharacteristic noetherian local domains. Thank you.
Thank you very much. And many thanks to the organizers for giving me this opportunity. Before going to the topic of the title, I would like to recall something with which everybody here is probably very familiar. We start from a valued field, and then we love to embed it into some field of generalized power series. This is Kaplansky's embedding. Its roots go back to the origins of valuation theory almost. And I'll be talking about the problem of local uniformization, where we start with a ring, with a local ring, whose field of fractions is k, so it's valued. And so it means that R is contained in some valuation ring of this field. And I'll always assume that the valuation is centered in R, which means that the intersection of the maximal ideal of R nu with R is the maximal ideal of R. Now, if you are interested in the problem of local uniformization, one tempting idea is to use this Kaplansky embedding to view the elements of the maximal ideal of R as series, and then use this description to invent ways of improving the ring R in such a way that you can build another ring which is still contained in the valuation ring, still dominated by the valuation ring, but now we want that R prime is essentially of finite type over R. That means it's localization of an algebra of finite type, and this is the important fact, regular. So this is the problem of local uniformization, and as I said, it's very tempting to use this Kaplansky embedding to attack this problem, which is still open in positive characteristic. Now, I want to begin immediately with an example which contains the gist of what I want to talk about. And it's the case where R is the polynomial ring in two variables, localized at the origin. And I'm going to describe a valuation, which is a classical example, going back to Teissier, but I'll give it a little twist. And the valuation starts as follows. You take an infinite sequence of rational numbers, which is constructed as follows. You take a sequence of integers. Sorry. We assume for simplicity that they're all larger than 2. The size are integers. And then you set gamma 1 to be, you choose some, let's say, S1 plus 1 over S1. And then you inductively, you define gamma I plus 1 to be Si gamma I plus some integer which you fix, satisfying certain conditions. I won't go into this, it's not very interesting. The important thing is the denominator, where you see that at each step, the denominator grows. So you build like that an infinite sequence of rational numbers, and they have the property, if you look a bit carefully, that Si gamma I belongs to the semigroup generated by its predecessors. So that means it can be written as a sum Lik from k equals 0 to I minus 1. Okay, this is not very inspiring, but you should look at this. You should look at the semigroup algebra of this semigroup here and think of it as a curve. Of course, it's not really a curve, but this is a ring of crude dimension 1. And you can think of it, as I said, as the curve given by ui equals t to the gamma I. Now, what do we do with this curve? The first thing to do is to look at its equations. And the equations are, if we know, which is true, that these relations between the generators generate all the relations between the gamma i's, then we can find a set of equations for this curve, which is u1 to the s1 minus u0 to the s1 plus 1 0, and then ui to the si minus the product of uk to the lik from 0 to I minus 1 equals 0. So this is an infinite set of equations, which is the set of equations for this monomial curve living in this infinite dimensional space. Now, how do we proceed from this to evaluation on this ring? Well, one way is to deform the equation. So this is a 1. And I go on, and every time I just add the next variable to the ith equation. Now, once I do this, I realize that I can eliminate all the variables because u2 is a function of u0 and u1. Then u3 will be a function of u0, u1, and u2, but therefore also a function of u0 and u1. And if I do this, what I get is, if I mod out, let's call these equations fi. If I mod out the polynomial ring for all those variables by the ideal generated by the fi's, I find that it has to be k of u0 and u1. Okay? So how do I get evaluation? Suppose that I stop at the ith step. That means I forget this, and I forget all the other equations. Then I get the equation of a plane curve, because I can eliminate, as I explained, but now in finitely many steps, I find a polynomial in u0 and u1, which turns out to be irreducible. And this gives me some equation, phi I, of u0 and u1 equals 0, which is a perfectly good plane curve. Now, if we are in characteristic 0, this is irreducible. As I told you, it's very easy to prove. Then I can use this to find a Puiseux expansion of u1 as a function of u0, something. And there I find that the denominator of the exponents has to be the product of the si's. So this is the Puiseux expansion for u1, which I get from the ith equation, which I got by stopping at step I, forgetting ui plus 1, and forgetting all the other equations. Now, it turns out that these power series, these are perfectly good Puiseux expansions if I'm in characteristic 0. And they converge as I tends to infinity to a series which is no longer a Puiseux expansion because the denominators of the exponents go to infinity. Because remember, the si's were all greater than or equal to 2. So what is the picture? The picture in the plane is that I get a sequence of plane curves, which are all distinct, which actually fill out the plane. And at infinity, I get some kind of ghost curve from the algebraic viewpoint, which is a perfectly good valuation, because I get a valuation by now looking at this u1 infinity. Because it is not a Puiseux series, it is not going to kill any polynomial in k of u0, u1, which means that if I take any polynomial p in u0 and u1, and I substitute u1 in it, I get a series in u0. Then I can take the order in u0, and this gives me evaluation. Because, as I said, this can never be 0. The set of exponents is, of course, well ordered. It gives me evaluation. And this valuation is a perfectly honest valuation on this ring, except that I should write it k of u0 and u1, u0, u1. Now, this is the prototype of the valuations which nobody loves really in algebraic geometry, which are called infinitely singular, or non-Abhyankar valuations. And suppose now that you are dealing with evaluation on a singular surface, because in this case, the problem of local uniformization does not arise because I started from a regular local ring. Now I can start from a surface, which has singularities, map it down to the plane in some way, and then take evaluation in the plane and lift it to the surface. And exactly the same story will go on. I will produce curves on my surface, real honest curve, and then in the end I will get a ghost curve as valuation of the ring of my surface. Now, the idea which I want to develop is that you can do this quite generally, and that if you are on a singular surface and you look at your curve, which are real honest curves, then if you go sufficiently far in the sequence, the resolution of singularities of one of those curves, of any one of those curves, will actually produce a local uniformization for the valuation on the surface. This is quite reasonable if you think about it. Because, well, here I'm cheating. But suppose you know that your curve, you make some kind of blowing up, birational map, whatever, so that the curve here becomes non-singular on the strict transform. And the strict transform of your surface then contains a non-singular curve. And if you can prove that this non-singular curve is cut out by exactly one equation, for example, on the surface, then the surface has to be non-singular. The idea is that it takes more equations to define the curve than it takes to define the surface. That's a pleonasm. And then if you resolve enough the equations of the surface somehow will have to follow. It doesn't really work like that. Let me reassure you. But it's an idea which it is good to keep in mind. So, but here, remember, I have used characteristic 0 in order to get Puiseux expansions. So in characteristic 0, we know very well, you know very well, that all these things, at least if I assume that the residue field is algebraically closed, all these things work very well. Now, what happens in positive characteristic? In positive characteristic, what happens is that the connection between, you see here, if I start with my infinite series, look what I've done, I've exactly done this. My infinite series here gives me exactly an embedding of this ring into the ring here. This is a Kaplansky embedding by sending u0 to t to the whatever I chose here, s1 plus 1, u0 to t, and then the ui's to t to the gamma I. So what I've done here, sorry, I send u0 to u0 and u1 to this series here. Then I get a Kaplansky embedding for my ring. And in characteristic 0, it's not difficult at all to extract from this Kaplansky embedding the characteristic exponents of the curves, and therefore the resolution of singularities of the curve. By truncation, whenever the denominator increases, you truncate, and you know that this is a Puiseux expansion for a curve, and then you only have to resolve the singularities of that curve. But in positive characteristic, the connection between what you see in your series here, supposing even it exists, which it doesn't in general, and what you need to know in order to uniformize the valuation, this relationship collapses. And the example is this. Oops. Oops. The example is this. Okay, look at the curve over a field of characteristic P. Look at the curve given parametrically by, sorry. Where is it?
Yes.
Sorry?
You have to read what you write.
Ah, excuse me. Okay. Nevertheless, t to the p cube and t to the p cube plus p squared plus t to the p cubed plus p squared plus p plus 1. So people who do singularities in positive characteristic know that in positive characteristic there is in general no Puiseux expansion like this, because in general you have two power series expansion and you cannot reduce one of them to just a power of t. But in this case, we have even a Puiseux expansion. Now, this describes a curve which has a certain ring O, which is of course contained in k, well, whatever. Let me take power series, k of t, by this O is k of u0, u1, let us say power series divided by some equation. And the semigroup of the t-adic valuation on O, gamma, in this case, is the numerical semigroup generated by p cubed plus p squared, and p4 plus p cubed plus p squared plus p, and p5 plus p4 plus p cubed plus p squared plus p plus 1. And here the important thing to notice is that while in characteristic 0 you have as many generators of the semigroup of values as characteristic exponents, in this case all I see is 3 exponents, and the semigroup has 4 generators. So something is going badly wrong. And we don't know many such examples, but they do exist. And what it tells you is that even assuming that we had a Puiseux expansion like U1 infinity there in positive characteristic, from that expansion you cannot easily deduce, or rather you can perhaps deduce, we don't know, information about the semigroup of values. This example shows that in any case it has to be complicated. So what I'm going to do here is to propose an alternative to the Kaplansky embedding in the case of noetherian rings. Because the Kaplansky embedding in positive characteristics seems to be a very complicated approach. So what is the alternative which one can propose? It relies very heavily on the fact that we are dealing with noetherian rings. So when I'm going to go back to my noetherian ring with its valuation, and I'm going to make an assumption which is not only that the valuation rings dominates the local ring, but that there is no residue field extension. It looks like a severe restriction, because we all know, for example, for divisorial valuations, such a thing does not exist. But these are the only really important valuations for local uniformization, at least from my viewpoint. If you can uniformize those, then you're done. So, and something very nice happens in this case, which is that we can define the filtration on the ring by the values which the valuation takes. So this gives me ideals like this. If, for the moment, I don't have to assume that my ring is noetherian. If my ring is noetherian, then here I can just replace strictly greater than phi by larger than or equal to the successor of phi, but I don't want to assume that just for the moment. So this gives me a filtration, and the filtration gives me an associated graded ring. Which is a subalgebra of the corresponding graded ring for the valuation ring itself, by definition. And now this person here has a very nice property that every homogeneous component is a one-dimensional vector field over k nu. So each of its components here is a one-dimensional vector field over k nu. This follows from the fact that if you take two elements in the valuation ring which have the same value, then they differ by unit. And if I look modulo greater value, I find this, but u bar has to be an element of the field k nu. So I have a vector space over K nu. This quotient here is a vector space over K nu in which any two elements are proportional. So it's a one-dimensional vector space over K nu. It can never be zero by definition of the valuation, but if I look at what happens on this subalgebra, this tells me immediately that this subalgebra is just the sum of certain of the homogeneous components of this ring. And which are those? They are exactly those for which the semigroup, the degree is contained in the semigroup of values. Okay? To be compared with the positive part of the group of values, which is the values which the valuation takes on the valuation ring. So this tells me that this algebra has the property that all its homogeneous components, which are non-zero, are one-dimensional vector space over K nu. But that means they are also one-dimensional vector spaces over K. And this tells me, this is an easy exercise, that this algebra can be presented as a quotient of a polynomial algebra by an ideal generated by binomials. This is strictly equivalent to the fact that every homogeneous component is subdimensional. And in fact, in the case where we have finiteness, like here we have finite rational rank, we can see that this algebra is isomorphic to the semigroup algebra of gamma over K, which corresponds to the case where all the lambda are 1. This is, sorry, UI. And where? Oh, here. No, this is a monomial. U to the ML represents a monomial in the variables U. And U to the NL, of course, also represents a monomial. Okay? So this is the connection between valuation theory and toric geometry. Because out of a valuation with no residue field expansion, we get, for free almost, a toric variety. Of course, this toric variety is not one of the usual ones because it has infinite embedding dimension. So pure algebraic geometers might not like that too much. But nevertheless, it's very helpful to think of it in this way. Okay, so what do we do with this? Well, let me give you a very simple example of evaluation which has this property and which is actually in phase with the example I gave above. Now I start with a very simple plane curve. So this is the equation of a plane curve. And of course, it has the ring of that curve has only one valuation given by the normalization. And the semigroup in this case, we can compute it. It's generated by 4, 6, and 13. So what does this have to do with all that? It's because if I look at the ring of my curve, now I take power series for reasons which, whoops, sorry, U0 and U1 power series divided by the equation F, which is here. Then the graded ring with respect to the unique valuation of O is, of course, this. But it can be viewed, there are two equations. This curve is a monomial curve. It's the curve t to the 4, t to the 6, and t to the 13, which lives in three-dimensional affine space. You notice that my curve lives in 2 dimensions and the graded ring lives in 3 dimensions. More generally, my ring can live in 2 dimensions and the graded ring in infinite dimensions. Like the example I showed you above, the valuation is on a ring of dimension 2 and the graded ring, which is the ring, the semigroup algebra of the semigroup gamma, is in infinite dimension. So, but here we are not going to such extremes. It's easy to see that these are the two equations defining this monomial curve, and that my curve here can be obtained from this monomial curve exactly by the method which I showed you above. This is an example of the truncation which I showed you out there. It shows that my plane curve can in fact be viewed as a deformation of a monomial curve, the monomial curve here. And not only that, but if you give to each variable the weight corresponding to the power it has here, corresponding to its valuation, you see that this has weight 12, this has weight 12, and this has weight 13. So I perturb my equations, my binomial equations, by adding a term of higher weight. This is what I call an overweight deformation, for obvious reasons. Now, what we are going to do is to try to generalize this to the general case here and prove that, in some sense, our ring R is an overweight deformation of the toric variety or the graded ring corresponding to the valuation. Why? Why? Because it's much simpler to deal with binomials than to deal with anything else in algebraic geometry. And here we have a source of binomials. So we are happy, even if they are infinite in number. Just means that we have to work infinitely harder, but that's okay. All right, so what do we do? Well, it's a general principle that, a general principle in commutative algebra, that when you have a ring like R, together with a filtration, like my filtration by the P phi, there is a specialization from the ring to the associated graded ring. However, in this case, this does not help us too much, because we don't know how to create the equations which describe this degeneration. If gamma is finitely generated, then there is no problem. Everything lives in finite dimension. We can produce equations. Everything is nice and beautiful. But here we are interested mostly in the case where gamma is not finitely generated. And then the general commutative algebra stuff does not help too much. So let me tell you a little bit. Nevertheless, there is something which we can get out of this. As I said, the cruel dimension of gr nu R is equal to the rational rank of the valuation. This is a result which is classical in the finitely generated case, and in the general case, it is due to Olivier Piltan. And then there is a famous Abhyankar inequality, which tells you, in this case, because we have no residue field extension, that the dimension of the graded ring is at most the dimension of the ring. If we imagine that we have a family where the generic member corresponds to R and the special member corresponds to gr nu R, and which is flat, which is actually the case, then this is a little bit disturbing, because we expect semi-continuity of the dimension of the fibers of a map. However, this semi-continuity is true only when you have finiteness, in which case it is true, but in this case we don't have finiteness. And the case which I showed you, the polynomial ring in two variables, the cruel dimension here is 1, the dimension of the polynomial ring here is 2, so we have exactly a case of strict inequality, and those valuations are called non-Abhyankar. The Abhyankar valuations is the case where we have equality. So we must remember this. So the postulate is that in any characteristic, the semigroup contains the information that is needed to uniformize the valuation. That is the basic principle. It is true for curves in any characteristic. The moral is Puiseux expansion does not, semigroup does. contain the right information. So forget about Puiseux expansion in positive characteristic and think about semigroups. Now, how do we extract this information? First step, the graded ring. The semigroup gives us these binomials, and we should be grateful. Now, how do we use these binomials? Well, first of all, I want to reduce, for reasons which will become apparent a little bit later, to the complete case. That means the case where our ring R is complete M-adically. Why? Well, for the reason which you will see in a minute. But in general, all the proofs of resolution of singularities, including characteristic 0, pass through the completion as some step. Because you want to use Weierstrass division theorem, because you want to use this or that, you complete. And then, as Michael Temkin says, you have to decomplete at some point. You have to prove that what you've done in the complete world actually comes from the algebraic world. And this can be non-trivial. And in my case, it is non-trivial. It corresponds to a very simple conjecture, which we don't know how to prove in general, but I will give you the conjecture in case you can find a proof. Conjecture is this. Suppose that I have a ring, R, and I'm assuming that the valuation is rational, low residue field extension, and I'm assuming that R is excellent. This is certainly an assumption which we need. I won't go into the definition. Just think of ring of algebraic geometry, and that's enough. Now, the conjecture is this. Nu is given. The conjecture is that you can find prime in R hat, which is the M-adic completion. So that the valuation nu extends. So this is an injection, because I want that R, H into R is 0. So it's a formal ideal. And the conjecture says that there exists an extension nu to evaluation of nu hat divided by H with the same value group. Sorry? I'm always assuming that, yes, same residue field. It's clear for rank 1, yes, exactly. It's clear for rank 1. It's true for Abhyankar valuations. This takes more work, but it's a conjecture in general.
Does it follow from the non-Abhyankar singularization?
Not that I know of. Okay, so I'm going to work modulo this conjecture. All right? Now, the next step, why do we want to use completion? It is because there is a very inspiring result, which actually has its roots in some work of Hasse and Schmidt on valued fields. And this is the Cohen, what is known as the Cohen structure theorem. It actually comes from an old conjecture of Krull, which necessarily is old, which Cohen proved. Actually, Krull had conjectured that any regular, equicharacteristic, complete local ring should be a power series ring. Regular, complete, equicharacteristic. You can't think of any other example. So Krull conjectured that this was true. And this was proved by Cohen in his paper, I think in 1951. But the important thing is this. Suppose that R is noetherian. Oh, I forgot to say noetherian. But at that time, regular implied noetherian. So noetherian complete, equicharacteristic. Before offer stops me, there is also a non-equicharacteristic version, but I won't go into this today. Okay. So noetherian complete equicharacteristic, local. Well, it's complete for the valuation. Then there is surjection so sending ui to some xi in R. This is surjective, continuous, of course, for the M-adic topology here and the maximal ideal topology there. And so the hard part of the proof, as Gohan himself notes in his paper, is to prove the existence of a field of representatives. And this has been a very active subject in commutative algebra for some time. But here we are going to sort of take that for granted, even though it's the non-trivial part of the proof. And we are really going to be interested in the following, that if we look at the graded ring of R with respect to the maximal ideal, then this is a quotient of a polynomial ring, because R is noetherian, so this is a finitely generated algebra over the residue field K. And so it's a finitely generated algebra, so it is a quotient of a polynomial ring in finitely many variables, which I will call capital U1 up to capital US, let us say, sending UI to some element xi bar here, which are the initial forms of some elements of R. Now, the important thing in this picture is that if I take generators from M mod M squared, that means a minimal system of generators for the maximal ideal of R, this is exactly the number of generators I need here, and this is exactly the number of generators in my polynomial ring, and this is exactly the number of generators in my power series ring, because I will send a UI to xi. And in order to define this map, I can send UI to any xi whose initial form in the graded ring is xi bar. So this is nice and clean. It's a beautiful theorem because it says that if you take any complete noetherian equicharacteristic local ring, then it's geometric in some sense. You can find equations for it. And what are the equations? The equations are some series here, f1 up to fc, let us say. And what do we know about these equations? We know that they have to be, their initial forms have to, I take generators here for the kernel of this. I can lift them to generators for the ideal, which is the kernel of the map upstairs. In other words, I can find elements of the ideal, which is this kernel, whose initial forms generate the ideal, which is the kernel of that map. This is very important because it tells us that my ring R, because it's complete, I can define it by, this will be a homogeneous polynomial plus higher order. So this is an overweight deformation. And now the project is to do exactly the same thing, replacing the ring R with its valuation nu and its graded ring, replacing R, the maximal ideal filtration, and the graded ring by my ring R, the filtration defined by the valuation nu. So this is called the valuative Cohen theorem. I erase the conjecture. I suppose it is simple enough that you remember it. So what is the statement? Now the statement wants us to be much more careful. Let me first define the objects. I start with my ring R, its valuation nu, no residue field extension. The semigroup gamma has a minimal system of generators because gamma is well ordered. Because R is noetherian. R is noetherian. If I had an infinite decreasing sequence of elements of gamma, I would have an infinite increasing sequence of ideals p phi, and that's not possible. So gamma is well ordered. This is absolutely fundamental. Another fundamental thing is that gamma is combinatorially finite, which is almost the same thing. It says that any element gamma can be written as a sum of other elements of gamma. The number of these is finite. Only finitely many ways of writing an element of gamma as a sum of finitely many distinct ways up to permutation of writing gamma as a sum of other elements of gamma.
Is it rank 1 or more general?
No, this is in general. This is in general. You can easily prove it by induction on the rank, for example. It's not a difficult fact. Okay, so these are the two things. From these two things, I'm going to build an algebra, which is the replacement, if you will, of the algebra of formal power series. Except that if you want to have a simple picture in your mind, let me first produce the algebra. So the algebra is produced like this. For any I, which indexes, so from gamma I remember the index. Oh, I forgot to say, gamma is well ordered, and its ordinal is not so bad. It's at most omega to the dimension of the ring. So it's not a very nasty ordinal. But still, you have variables. You must learn to work in a space where you have variables that are indexed by an ordinal. That's life. To each gamma I associate a variable. So I have a set of variables indexed by an ordinal. Now, with that, I build an algebra, which is the set of all possible sums where E is any set of monomials. So the exponents are allowed, and the coefficients dE, of course, are in K. So now the combinatorial finiteness is there to tell me that I can multiply two such objects. So it's an algebra. And it turns out this algebra has a number of nice properties. You can really think of it as an algebra of power series. First of all, it is local. Everything I'm going to say has to be proved, because everything is almost obvious in the rank 1 case, but in the case of rank greater than 1, you have to prove. For example, if I take a sum of series like this, take a sum of objects like that, an infinite sum, of course. When does it exist in the ring? Well, it exists if and only if each monomial appears only finitely many times. So this you must keep in mind always when you make an operation. You must check that each monomial appears only finitely many. For example, take a series without constant term. And look at the sum of h of u to the a for a in n. Okay? Does this belong to the ring? Yes. It's obvious in rank 1, but in rank greater than 1, you have to prove something, because you never know what could happen. The way the power is mixed, you have to prove something. But still, it is true. Then this implies that my ring, which I call E of gamma, for reasons which will become apparent, E of gamma is a local ring. And of course, the maximal ideal is a series without constant term. Next step. The fact that gamma is combinatorially finite says that every series like this, if I look at the terms of lowest weight, so the weight of a monomial, I should have said, is, of course, each variable has the weight gamma I, and the weight of a monomial is computed with multiplying by the exponents. Okay? So combinatorial finiteness means that there are finitely many monomials of a given weight. So, for example, if I look gamma being well ordered, if I take a series, there is a smallest weight, and the set of monomials with that smallest weight is finite. So the initial terms of a series like this is a polynomial in the use, which tells me that the associated graded ring with respect to the weight of E of gamma is just the polynomial ring in the UIs. Okay, now we're getting closer. Yes.
So, but it is clear when they are in the pair, it's clear that the geometric series.
That is true, yeah.
But when you want to go to the image,
Yes.
then you have to pull something.
Yeah, exactly, yes. But it is true.
Okay.
Another thing which is nice is that you have a weight, and therefore you have an ultrametric. I follow the convention of Franz Victor, which says that if I take two series, let us say A and B, I define the ultrametric distance of A and B to be the weight of A minus B. Of course, if it is rank 1, you would put E to the minus the weight, but it's much more convenient to use this. So you have an ultrametric on this ring, and the other result, which is not difficult to prove, is that E of gamma is spherically complete. So I guess everybody knows what it means. Any system of nested non-empty balls indexed by any ordinal without a last term has a non-empty intersection. So everything you can think of will converge, or at least in the sense of pseudo-convergence, in the sense of Ostrowski. So as I said, this ring E of gamma has all the nice properties of a power series ring, except that it's a little bit exotic concerning the variables. There is a natural map from E of gamma to the series, which itself lies, because these are series whose set of exponents is well ordered. I told you that gamma was well ordered, so the series with exponent in gamma, there is a subring in there. And my ring R, if I look at the Kaplansky embedding, I want to send it here, but what I really want to do is to present it as a quotient. So instead of presenting it as a subring of a generalized power series ring, I want to present it as a quotient of a generalized power series ring, but generalized in a different meaning. Non-Puiseux inspired generalization. Okay, so this is the basic idea. And why do I want to do that? Because here I have, if I take graded rings, I have a polynomial ring. And here I have my graded ring. And this map, if I look at the associated graded rings, it gives me this map. And on this map, I know the kernel. It's given by binomials. So all this is to justify the statement of the valuative coherent theorem. Excuse me? Oh, this is, excuse me, my writing is really not improving with age. This is phi positive, non-negative. The part, non-negative part of the totally ordered group phi of the valuation.
What's the definition of this formal series using more well-ordered?
Oh, yes, well-ordered exponents. So that you can have evaluation. So what I'm going to say is a sort of description of this rational valuation like this. So the theorem says this. Pick generators, Kraya bar, generators of the, I'm still in the situation as always. R new, no residue field expansion. R is noetherian complete. This is important. So generators of the K algebra gr nu R. So I have one generator, exactly one generator, I mean at most one generator in each degree. Okay. Then the theorem says, and look at the algebra E of gamma. The theorem says there exists, it's quite different from Cohen's theorem, there exists representative xi I in R such that the map ui to xi I induces a surjection induces a continuous surjection from E of gamma to R. So I just send here ui to xi I. You must see immediately that there is a problem. Because in this ring, for example, the sum of all the ui's, that converges in this ring. It's an element of the ring. But this must go to the sum of xi I in R. So this sum must converge in R. So it's okay if the rank is 1, because there is a beautiful theorem of Chevalet which tells us that necessarily, in this case, the xi I must belong to higher and higher powers of the maximal ideal. But if the rank is not 1, you could make a bad mistake, because you could take as xi I something which is nice plus always the same thing of higher, infinitely greater value, and then the sum makes no sense. So the part of the statement of the theorem is that you can find such xi I. And as I said, in rank 1, anything goes, but not in higher rank. So this is the first part, that there exists a continuous surjection like that, which induces, such that when you pass to the associated graded ring, it induces K, the presentation of the associated graded ring, gr nu R. And therefore, I know the kernel here. So that's the first part. The second part of the theorem tells you about the kernel of this map. So this is surjective. Let me call it pi. What is the topologies? Oh, here the weight. This has a weight. And here I have the valuation. The weight is, I defined it somewhere. The weight of each variable ui has weight gamma I. And this gives me a weight on the series of E of gamma. So the first part is the existence. The second part is that, again, there exist overweight deformations. No, this is in any rank. Rank 1, as I said, it's easy.
No, but the weight is in the value.
Yes, the weight is in the semigroup.
The semigroup.
Yes.
The topology is induced by.
Sorry?
The topology is the order topology. This is the order topology.
No, the topology is precisely the topology given by the weight. That is the one which I write here. This is an ultrametric. So two objects are close if the weight of the difference is large. Now you can, because if rank is greater than 1, then you have to be careful about what you mean by large. But we know how to deal with that. Okay? It is a topology which is not so usual, but it really makes sense. It makes sense, and you understand exactly what happens when you prove that E of gamma is spherically complete. Now, yes, as I said, yes, because there are only finitely many monomials of a given weight. So if you take any sum, you start at the lowest weight, finitely many, then you remove them, you look at the next, finitely many, and this gives you a procedure to write transfinitely your series. And that is what a series should be. I see that Florian agrees. So it is these sums are transfinite sums, and the topology is an adapted topology for these transfinite sums. So that you can have that two series are infinitely closer than two other series. And so what? It is still a topology. Okay, so let me finish because I don't have much time. The second part of the statement is, again, there exist overweight deformations of the monomials which generate the kernel here. Remember that the kernel is binomials. Sorry. So I write for Zoe, binomial, u to the mn minus lambda l, u to the nl. Lambda l's are constant in the field, plus sum of cp to the up, where u to the p is a monomial whose weight is strictly larger than the weight of any of these two terms because they have the same weight, which involve only finitely many variables and such that if I call this FL and the FLs are the kernel of my map pi. So what does this mean? It means that I take the ideal generated by the FLs, but because I'm in a topologized algebra, I have to take the closure of this ideal. This means I take infinite sums of combinations of the FLs. And the important thing is that my kernel up to closure is generated by overweight deformations of the binomials. This is really the important thing. Now, what does one do with that? I have only a few minutes. Well, there are many other things that one can prove. You see, the two facts here one uses very strongly the fact that the ring is noetherian. One uses versions of Chevalet's theorem for modules. Here one uses again very strongly the fact that the ring is noetherian. But that's not all. In fact, you see, this map is surjective. Here we know that we have finitely many generators for the maximal ideal. So it means that all the psi I which I have chosen, except maybe for I not in a certain finite set, they can be expressed as series, let me say AIK, psi k, where now the xi's are with indices in the finite set of generators of the maximal ideal. This means that ui minus sum of AIK UK, well again this involves finitely many variables, this must belong to the kernel. So this tells me that infinitely many of my, so this implies, it's easy to prove, that among the FLs, for each I which is not in the finite set here, this is not in the finite set, for each I which is not in the finite set of generators, for example, or any finite set generating the maximal ideal, the variable ui must appear linearly in one of those equations. And in fact, you can even prove that by changing generators, you can have infinitely many equations which are like that. So this is very encouraging, because if you could prove not only that there are infinitely many equations which are like that, but all equations except finitely many are like that, then you are in a very good situation, because finitely many equations involve finitely many variables. Finitely many variables means toric variety in finite dimension. We know how to resolve the singularities. We know that case very well. So all we have to prove is that all but finitely many equations are like that. And this turns out to be, I think, true, although it is not written up. So it provides an approach. I'm not claiming that the theorem is proved. I'm claiming that some good parts of it seem okay, but we still have the conjecture, which I mentioned at the beginning, which is open. But this seems to be a more, say, amenable approach to understanding how to uniformize valuations on R than the Kaplansky embedding, which has all these difficulties which come out from the bad behavior. Again, I insist, because we don't know anything about that, I think, in general. The bad behavior of the relationship between power series expansion of variables and semigroup. And I think my time is up.